Hello and welcome to the Conservation of Energy Dart Gun video tutorial. Here we've got this gun and it's going to be fired straight up, and the spring will release the ball and the ball will shoot straight up, and we are going to solve for the height of the ball when the ball is moving at 12 meters per second. So we're going to start with an energy bar diagram, which we have ready to go down here, and we're going to fill in the bars where they go. So before the gun is fired, we're going to say the ball is at 0 position, so that means there'll be no EG. The ball is not moving, so there'll be no EK, and where is it? Right there. Ignore air resistance. So E internal is most likely out of this problem entirely. So we're looking at 100% elastic energy because that is the spring being loaded right here. Once the ball is fired, it's going to be up in the air. The spring will be fully discharged, so there will be no more elastic. The spring will be moving. So, or not the spring, sorry, the ball will be moving. So we do have EK. And the ball will have some height to it now, so there will be EG. At the moment, we don't really know which one of these is going to be more. We're going to have to solve the problem to figure that out, and then we'll come back and adjust these later so that they're correct. But at the moment, we are content to just go along and do this. So before the gun fires, we have all elastic. So we're going to say all elastic. And that's going to be equal to whatever we have after the situation. So we have kinetic energy, and we have gravitational energy. All right. So the next step is to just replace what we have here with their equation. So elastic energy is 1/2 K x squared, and that's going to be equal to 1/2 mv squared plus mgh. All right. In the next step, we are going to plug in all the values that we have. Actually, you know what we'll do instead? Why don't we isolate h first, and then we'll plug everything in. So to do this, we're actually going to make an equation because it's going to get a little crazy. So we'll start with, and I'm going to change these 1/2s actually to 0.5s. So we're looking at 0.5 kx kx squared, and then we're going to subtract this stuff over here. So minus 0.5 m v squared. So that's bringing this over to this side of the equation. So it would be this minus this divided by the stuff out of this. So we're going to divide out the m and the g. So divided by mg. And that's going to be equal to h. So now it's a matter of plugging everything in. So we're going to look at 0.5. Well, we know we're going to have a fraction. So actually, why don't we start with h too? H equals, and then we're going to end up with a fraction. 0.5, let's see what k is. K is 2 kilonewtons per meter, so that's 2,000. Times something squared. Let's see what we got squared. The x value. Well, it says that the equilibrium point is here at point A, so it looks like this right here is how much the spring has been compressed. 0.15 meters, because we got to change that to meters. So milli means 3, so 1, 2, 3. 0.15 meters. And minus, let's see, 0.5 again, the mass. Let's see, the mass was 175 grams, that's 0.175. And the velocity was 12. And all that's going to be over mass times gravity, and the mass is 0.175 times 9.8. All right, that's the matter of solving it. So I'm going to do this in more than one step. H equals, we'll keep the fraction for now. So let's see, 0.15 squared times 1,000, because that's half of 2,000, is 22.5. And 144, which is 12 squared, times 0.175 times 0.5 is 12.6. And 0.175 times 9.8 is 1.715. That means our H is equal to 22.5 minus 12.6, which is 9.9 divided by 1.715 gives 5.77 meters. So that is the height of the ball if this was to be shot straight up when we are moving at 12 meters per second. So really quick, just last thing to do is to figure out which one of these two bars should be larger. So let's just do that, maybe down here. So EG is equal to MGH, which is, I'll just do all this on a calculator one shot, 0.175 times 9.8 times 5.77, and I'm going to get 9.896, 5 repeating. All right, and EK, whoops, that's not what I meant to do. There we go. EK, I'm going to hit Control K. EK is equal to 0.5 mv squared. So let's see, 144 is v squared times 0.175. Actually, I don't, it's 12.6. Look, right here. Boom. Boom. 12.6. 12.6. So it looks like the EK is larger, so it looks like our diagram checks out. And maybe it's not twice as large, but at least it's larger. So qualitatively, this is a correct energy bar chart. Thank you for watching the Conservation of Energy Dart Gun video tutorial.